As we wrap up Chapter 7, we're on our last section, 7.8, which is Advanced Factoring Techniques. And we're going to address two different objectives. The last two are 25 and 26. 25, we're going to factor polynomials using grouping and chunking. And then 26, find all real solutions of a polynomial by factoring. So let's just dive right into them. In the notes, we're going to do two examples of factor by grouping, which you did do back in Algebra 2X. And the best way to approach it is this, you're going to try to find two variables that you can actually group together and pull greatest common factors out of. And there's actually two different ways you could do this one. A lot of people will cut it down the middle and try to find something you can pull out of here and then something out of this one, which does work nicely. If we do that, the first two terms you can pull an x or a t squared out of, which leaves you with t minus 3. And then from the next two, you could pull out a negative 4, which will leave you with a t and then minus 3 again. Now, be careful. If you had just pulled a positive 4 out of here, what would happen is you're going to have the sign issue here is not going to match. You'd end up having a t plus 3, which is not what you want. Because once you've done factor by grouping, you really have, this is one big term and another big term. And if you can notice, these are like terms right here. This is the same here and here. So pull it out of both. So pull out the t minus 3. What you're left with now is going to be this part and this part. So you just put t squared minus 4. Now, to continue factoring, you want to think about, can you fully factor t squared minus 4? Remember, if you want to look at it this way, what you have is t squared plus a 0t minus a 4. Factors a negative 4 and 1 that add to 0. This does factor nicely. This will factor into t plus 2, into t minus 2. If you were to do the distribution on these two binomials right here, you would get this second degree binomial, so you can double check it. I teach my Algebra 2 kids to check this, what I call a nose and a mouth. If you do the multiplication of those two terms, it will be your middle term, in this case, is 0. So we have a positive 2t and a negative 2t, so that does work. And then don't forget to bring this factor down also, which is going to be t minus 3. So when you factor by grouping and completely factor, these are the three binomial factors that we get for t cubed in this polynomial right here. I do want to show you, though, that you could have factored by grouping a little differently on this one. You could put these two terms together and then these two. If you do the t cubed and the minus 4t, you would pull out here a t, so you'd have t squared minus 4. And then if you have the negative 3t squared plus 12, what you could pull out of this would be a minus 3, then you would have t squared minus 4. And then factor by grouping, you would pull this out, and you'd have the t squared minus 4 and the t minus 3. And then you would just finish it off as you did on the previous one by completely factoring this. So sometimes there's more than one way to factor by grouping, and either approach is going to get you the same answer. Now again, back on that first slide, when we factored this particular third degree polynomial, this is what we got. In the upper right hand corner on that slide, it says use the results from our example to solve the equation. So before they just wanted us to factor this expression, now they've added equals 0 and they made it an equation, so solve it. To solve it, all you need to do is come up with what we had for the factors that these were. And we did. We got the factors, right? That was this. And then to solve it, just take each of the three factors, set them equal to 0, and solve. So we know t is either equal to negative 2, a positive 2, or a negative 3. So you can easily solve that. By the way, if you were to graph this function right here in your calculator, what you would do is you would see it has 3 real x-intercepts, or 3 real zeros, at these particular points. So the factoring and solving of it will give you the actual zeros or the x-intercepts of the graph. So I want to have you try a second example on factor by grouping, but try it on your own. So pause the video, give this a try, and then when you're done trying it, restart the video and see if the problem matches exactly what I have done. So good luck, and why don't you pause the video. Now when you fully factor, here's what you're going to get. Again, this is a third degree polynomial, which means it has up to 3 real zeros, or 3 factors, and we actually did find 3 real factors. Now, if this had asked us to solve the equation, the difference would have been this. It would have been equal to 0. And when you solve it, you would take each of these 3 factors, take that, this, and set them equal to 0. So the zeros of this function, if we put this in the graphing calculator, it's going to cross the x-intercept at 5/3, at negative 2/3, and at positive 2/3. Now this next technique is one I don't think you've ever done before, and it's called chunking. It's pretty clever in that if you look at this particular expression, it's quite involved. This will end up being a 4th degree polynomial, by the way, if we were to do all of the multiplication out, but we're not going to. Here's what chunking does, is you're trying to look to see if there's anything that's similar. And right here we have an x squared plus 4x and an x squared plus 4x. And what you're going to do is they call substitution. So what I want to do is I'm going to actually say, let the letter u equal x squared plus 4x. And I'm going to substitute that in for wherever I see it, just to make this thing look more simple. So if I do that, I'm going to have u squared plus 7u plus 12. Now when I look at that, this is actually quite easy to factor. This factors very nicely. Factors of 12 that add up to 7 would be plus 4 and plus 3. And that is actually completely factored. But before you finish this problem, you have to realize that u wasn't in the original problem. The letter u we actually replaced with the x squared plus the 4x. So you need to put x squared plus 4x back in where you see u. So go ahead and do that. So we have the u here. I'm going to put the x squared plus 4x, and then don't forget plus 4. And then here x squared plus 4x again, and then plus 3. Now before you call this a final answer that it's fully factored, take a look at what's left over and see if you can factor any more of these 2 trinomials. Are there factors of 4 that will add up to a 4x term? Are there factors of 3 that will add to 4x? If you do this, this first trinomial can actually be factored into x plus 2 and x plus 2. And we will get x squared plus 4x plus 4. Also, this here can be factored into x plus 3 and x plus 1. So in doing this, you look at it now, remember when I told you earlier this is going to be a 4th degree polynomial. If, again, I were to multiply that out, you're going to have the highest power is going to be a 4th power, which means a 4th degree polynomial has up to 4 real zeros, thus 4 real factors. These right here are the 4 factors. Sometimes when you factor, you're going to get imaginary numbers, and you're not going to get nice real ones. The point of this section is we will have some nice real factors. If you don't, just stop. So we're going to factor over the real coefficients. And we're done with that one. Now, this one can actually also be done by chunking. It's not as obvious as the first problem was. That first problem clearly showed us an expression that were similar. There is something here that's similar, and I'm going to tell you this. I'm going to be able to, if you see the connection, chunk by x plus y. That's the whole group. So I'm going to end up saying let u equal x plus y, which means I need to have other groups of x plus y. This right here can be factored right now. If you just factor what's embedded in here, you can factor this into an x plus y times an x plus y. You could check it, by the way. This right here is a xy, another xy, which is 2 xy's. Okay, so we have that, and then I'm also going to put plus the x plus y minus 2 equals 0. And I'm going to rewrite this as x plus y all squared plus x plus y minus 2. Now it looks like it's nicely ready for chunking. So go ahead, and we had said u, again, is going to be equal to the x plus y. So find the x plus y and put u in its place. So this is u squared plus u minus 2. Can we factor this? It does work quite nicely. Again, we're going to have u, factors of negative 2 that add up to 1u. So I would have to do a plus 2 and a minus 1. So double check it. That would be a 2u and a negative 1u, which would be the 1u right here. Okay, so it's fully factored, and now I need to put back in there the x plus y, what we started with. So u is x plus y, so I'm going to put x plus y, then plus 2, and then an x plus y and a minus 1, and then we get that equal to 0. Now, these problems here, this one says draw the graph, and I'm not going to have us go that far. I just want you to understand and see how you could use a factor by chunking. Now, these last two slides are going to address the last objective, which is find all real solutions of the polynomial by factoring. So the real solutions are the ones where if we graph it, we would see the x-intercepts. They're the real answers. This right here is x to the 6th equals 1, which, by the way, if we get everything on one side, would be y equals x to the 6th minus 1. That's what you could put in the graphing calculator, and that's what they've done here, is they've just brought everything to one side. And you graph it. When you graph it, you're going to actually see where the zeros happen. They happen at 1 and negative 1. Well, if I know the zeros are there, I can expect that the factors are at x plus 1 and x minus 1. And what they want you to do is find all real solutions by factoring. And you might think that you're done, but I expect more for this problem. I want you to fully factor this problem. And when you fully have it all factored out over the real coefficients, which means no imaginary factors, you will end up seeing that these two factors happen. Now, I'm not going to do long division. What I'm actually going to use is a chunking method for this. And let me show you how chunking can actually work pretty well. And what I would do, again, let's just take this. Let's do the x to the 6th minus 1 equals 0, okay, or equal to y. If I factor this, what you could do is this. You can either realize one way you can break this out is just equally divide your x to the 6's, so x cubes squared minus 1. Now, if we were to do chunking, by the way, you would say, well, let u be x cubed. You'd have u squared minus 1 equals 0. Well, u squared minus 1 is just u plus 1 and u minus 1. Okay. Well, because we said u was x cubed, what you could do is just write an x cubed plus 1 and an x cubed minus 1 equals 0. Now, some of you are going to see this and just know you can take this x to the 6th power and cut it right in half and go right to this for factoring. That's fine. But they teach you chunking because they know that you're comfortable factoring u squared minus 1. And how can you do that is you could set it up like this. Okay, now we need to completely factor this. Recall that we did the sum and differences of cubes in the previous chapter. So you're going to want to revisit the sum and differences of cubes. I'm going to pause the video and put the formula for the two cubes up here, and then we're just going to apply the formula and break this down and break this down by the sums and differences of cubes. So just let me get the formula written. Okay, these were the two formulas we learned back in 7.7 for the sums and differences of the cubes. So if we go ahead and completely factor this, here's what it's going to look like. Let's start with the x cubed plus 1. We're going to use this one here. Our x value in this case is an x, and the y value is a 1. So if we bring that in, we're going to have x plus 1, and then we're going to have an x being squared, minus an x and a 1, and then plus the 1 being squared. Okay. Let's do this differences of cubes, and that's just this formula here. Again, our x here is going to be just the x, and the y here is just the 1 from our original. And let's just continue to factor that. Again, I'm factoring this component here. So that's going to give me an x minus 1. Then I'm going to have an x squared plus, I have the x times the 1 plus a 1 squared. And if you simplify this down, what you're going to get is x plus 1. Let's clean this up. X squared minus x plus 1, and x minus 1, and x squared plus x plus 1. So this right now, this 6th degree polynomial, is actually factored over the real integers. This trinomial right here is not factorable over real numbers. What you'd have to do is the quadratic formula and find out that there's imaginary solutions. The same with this. This is not factorable over the real numbers. You can't just do nice factoring. So what we've done is it says this, part A, find all real solutions to x to the 6 equals 1 by factoring. And we did find the real solutions. They're right here, and they're right here. To find the actual solutions, though, right, you would just say x plus 1 equals 0, x minus 1 equals the 0, and you'd say x is equal to 1 and negative 1, which we clearly were able to see back here in the actual graph. Now, they do want us to do part B, which says use the result from A to find the non-real solutions. The non-real solutions, again, are going to be these two trinomials. So I want you to just take one of them and try doing the quadratic formula. I'm going to go to the next slide and set the quadratic formulas up for both of them and show you the actual answers or the roots that we get. So what we've done is we took the original problem, which was x to the 6th equals to 1. We clearly knew that there were two real zeros of 1 and negative 1, but it's a 6th degree polynomial, so there's actually 6 zeros. The other 4 are imaginary. Imaginaries happen in conjugate pairs, so these are another 2, and this is another 2, giving us the final 6 zeros of the entire polynomial. Now, this last problem in the notes is just another example of what we did above. So I'm going to challenge you to find all the real zeros to this particular problem by factoring, and then use the results in part A to find all of the non-real zeros. So very similar to what we just did. Why don't you pause the video and just take a look at part A, and then I'll pop that up and we'll talk about it, and then we'll look at part B real quickly. So go ahead and pause it and try doing this problem similar to the last slide. Okay, if you take a look at the work that I did for part A, find all the real zeros. Again, I moved the 289 over by subtracting it to both sides. And then you can either do chunking on this or just notice these are perfect squares. You can chunk it and you can chunk out x squared. That's what I did here is I let u equal x squared, and then you would get u squared minus 289. You can factor that nicely into u plus 17 and u minus 17. And then put the x squareds back in and get this right here. Or if you see it, you're more than welcome to realize x to the 4th can be evenly split as the 2 single x squareds, which is right here and right here. And then 289 is a perfect square of 17, so it would actually work quite nicely. You can double check this, by the way, see if this middle term here would zero out, because there is no middle term for this particular polynomial. Now, they do want us, it says here, find the real solutions. They didn't necessarily say show the factors, but they want us to find the solutions by factoring. So what we've done is we can actually take this one right here, this particular factor, set it equal to 0, and that's going to give us 2 of the real solutions. Now, if we were to continue on with this one, part B says use the result from A to find the non-real solutions. We can go ahead. You can either do part B, finding the non-real solutions. You can use the x squared plus 17, and you can either set it equal to 0, or you could set it up in the quadratic formula. If you set this equal to 0, you're going to get x squared equals negative 17. Take the square root, so it's plus or minus, and this is an imaginary number, so it's plus or minus I, the square root of 17. Here are the other 2. Again, imaginary answers travel in conjugate pairs. So we know that there's four roots for this problem. 2 of them are real, 2 of them are imaginary. There can be no more than 4, so we found them all. Now for the homework, I don't want you to do anything in the book on here. Look in your note packet, and in your notes packet, there's written down numbers 1 through 5. I want you to factor these fully. You don't necessarily have to find the zeros for them, but factor fully. The first 2, I suspect you can factor by grouping. The next 2 would be a factor, probably by chunking. And the last one, I want you to factor fully x to the 8th minus 1, which is like this third example that we did today. So good luck.